Okay, so it's my pleasure to introduce our next speaker, Dr. Joshua Vogelstein, who's an assistant professor in the Department of Biomedical Engineering at Johns Hopkins University, with joint appointments in applied mathematics and statistics, computer science, electrical engineering, neuroscience, and biostatistics. He works in the field of biomedical data science, focusing on the statistics of brain networks or connectomes. So Joshua first completed a bachelor's degree in biomedical engineering at Washington University, before going on to complete a master's degree in applied mathematics and statistics, as well as a PhD degree in neuroscience at Johns Hopkins University. He then gained further training in mathematics and statistics, both at Hopkins as well as at Duke, before beginning his own lab, where his research focuses on developing new statistical methods and computational tools to map patterns of connectivity in human and non-human brains. And in addition, a key research goal is to understand and improve animal and machine learning. He's published extensively on this and related topics, and in 2020 was awarded an NSF Early Career Award. In 2011, he also co-founded the Open Connectome Project, and a few years later, Gigantum, which are both projects or platforms that facilitate open science. So it's a great pleasure for me to welcome him here today. His talk is entitled Lifelong Learning, Theory and Practice.
Thanks,
Andrew. So over to you.
Well, there's a bad echo for me right now.
Definitely a bad echo.
How about now? Still bad. Does that fix it?
Josh?
Yes.
Do you have more than one window open?
I do not, but I will close everything else.
Ooh.
Okay, how about now? Okay, great. Interesting that the debugging didn't pick up on that, but that's okay. Okay, thanks everybody for coming. Thanks, Andrea, for that wonderful introduction. For those of you who don't know, Andrea was actually one of the first people ever to train me. So when I was doing my undergrad research, Dora Angelaki amazingly accepted me as an undergrad researcher into her lab, and Andrea was a postdoc. And so my first training as a research scientist was from two fabulous women. I'm so grateful to have been started on my path with them, and I'm so grateful to be reconnected with Andrea again. And I'm grateful to be here, excited to talk about this stuff. For those of you who've seen this talk recently, I'm sorry. I like this content, so I'm talking about it again. So the title I changed slightly to Lifelong Learning and Beyond, and you'll see what I mean. And so I just want to start with what is learning, and this isn't quite going to be interactive, so I'll just tell you a few definitions that I've found in the literature or online. Google defined it, at least in 2020, the acquisition of knowledge or skills through experience, study, or being taught. About 20 years earlier, Tom Mitchell in his book defined it as a computer program is set to learn from an experience E with respect to some task T and some performance measure P, if its performance on T as measured by P improves with experience E. And I essentially reworded that to be simpler for me, which is F learns from data D with respect to tasks S when its performance at S improves due to D. So here's what I mean by learning. And it turns out there's lots of people who have tried to formally define learning. The earliest examples I know of this are from a pair of Russians, actually, Klivenko and Cantelli, who published articles in 1933 in this book from Definetti, where they talked about convergence probabilities and estimation. Vapnik then kind of rediscovered that work, and Valiant also later rediscovered that work like 50, 60 years later. And they have some really nice formal characterization of what learning means, and that's kind of the foundation of pack learning theory, which is the foundation of computational learning theory and machine learning. But there's some real limitations with those approaches. And so I argue there's an impedance mismatch between the informal definitions of learning and the formal definitions we have. The informal ones are intuitively pleasing, at least to me. They really characterize what I mean when I say learning. But they're not meaningfully formalized or operationalized. The formal ones are formalized and operationalized, but they make a really, really strong assumption that is never true in any of our data sets, which is that the training distribution and the testing distributions are exactly the same. And you know that's not true just by simply virtue of the fact that one of them is generated for training. And so there's a whole bunch of curation and all sorts of other stuff that went into the training that in general won't be on the testing. Also, time passes, things change, even if it's images, cameras change, formats change, all sorts of stuff. So in general, the training and testing distributions are not going to be the same. And then the other issue with many of the formal definitions of learning is that they only consider one task and one data set. And in modern machine learning challenges, we have many tasks and many data sets. So the goal of this talk and a lot of our recent work is to come up with a framework that has the following 4 properties. One is we want to formalize our intuitive understanding of what learning is. Then we want to include many different kinds of learning scenarios, so it kind of encapsulates the current field. We'd like it to enable rich theory that can provide insight to how to design new algorithms, and also then guide practice for actually build those algorithms. Okay, so we're introducing something called adaptive distribution learning theory. Lots of people have been talking about adaptive distribution learning recently. The key insight to formalizing all this stuff from our perspective is that we want to decouple the training data distribution from the test or evaluation data distribution. And then we also are generalizing it to include multiple data sets and tasks. So I hope this is going to be familiar to most of the people in the audience, but just to walk you through it, in a classical machine learning task setup, we have X's are observations, Y is going to be actions or labels, S is a setting, which is kind of fixed in classical machine learning, and then T is going to index the sample. And so what we're going to get is this trained model G hat, and it's trained by this learner F, which eats all the data and spits out some model. And then there's some loss function, which eats all the test data and the trained model. And then we can evaluate our trained model with the risk. And what the risk does is this integrates the loss with respect to all possible test data corresponding to the distribution that it was sampled from. And this is how we evaluate a particular model. But then we have the error because we want to actually integrate out not just the test data, but also the training data, because we don't care about that particular training data, but we care about, in general, the training data. And so we have error, and the goal of a machine learning task is typically to minimize error subject to constraints. And what you can see is we're just integrating the risk with respect to the possible training data. And this is integrated with respect to the distribution of training data. And expanding this risk out, you can see it's all in there. And the key is there's these 2 integrals, but they're both with respect to the same distribution, which is the distribution of the test data and the training data. Now, in this, we assume that S is the same. It's the same setting because there's only one task, and the training test distributions are necessarily the same. If we change that, stuff gets way, way harder. Okay, so given all of that, we're just going to define learning. And so we introduce this notion called learning efficiency. And so what we're going to say here is that D naught is the knowledge prior to acquiring any data at all. So typically, like our priors and our constraints and the inductive biases aren't really thought of as data, but they are. They're data from our brains that we put into our algorithms. And so we can call them data if we want. And so D naught is all of the knowledge that we have from the world that we've used to build the algorithm. And then D1 is just some training data, and F is the learner. And so what we're going to say is the learning efficiency in this setting S for this algorithm F is this ratio of the performance when it had no data divided by the performance when it has some data. It's this training data. And what we're going to say is F learns with respect to task S from the data if the learning efficiency is bigger than 1, or if its log is positive. And so we'll say it positively transferred. This also enables us to define forgetting. And we can say F forgot if this ratio is less than 1 or the log is negative. I just want to point out that these definitions are kind of global, but one can locally learn and globally forget. For example, let's say I learn one new word, but I forget 2 when I learn that new that one new one. Now I've globally forgotten. I'm going to do worse at some language task. But locally, I did add a new word. And vice versa, right? You can also forget one thing that helps you remember two things, hypothetically. And so what I want to say here is that F, this algorithm, transferred information from the data set into G hat, which is the hypothesis or our model. And that's really what's happened. It's really transferred information from the data. And so that's going to be important because now I want to revisit our goals and show you how this kind of formalism can include all sorts of different learning scenarios, including transfer learning. So here, in transfer learning, we have one task, but now we have multiple data sets. And so D1 is the data associated with this task. So let's say we're trying to train whatever, some confidant on classifying cats versus dogs. And so D1 is all the images of cats and dogs and their labels. And then D is all the data. Let's say we have all of ImageNet and all of CFAR and all of Flowers 101 and all those other things. Now we want to measure if the OOD data, this out of distribution data, the things that aren't cats and dogs, helped performance over just the task data. And so we're going to quantify learning efficiency. It's going to be the ratio of how well did it learn when we just use the task data divided by all the other data, all of the data. And we say F transfer learn with respect to this task if using D/D1, meaning the parts of D that aren't in D1. Sorry, the parts of D that that don't include all the elements of D1, if that log is positive. So in other words, if the other data, the non-D1 data, improved performance, made the error go down more, then it's transferred from that data for this task. And when I say it, I mean F, this learning algorithm has transferred. Now, multitask learning is more or less a generalization of transfer learning. We're going to have multiple tasks and multiple data sets, and so DS is the data for each task, and D is all of the data. And that may include some other data that's not associated with any task. And we're just going to say we're going to measure transfer learning for every task in exactly the same way we just did. And we say that F transfer learn for all tasks, for task S, if the log of the learning efficiency is positive. And if we have a weighted average of all the log learning efficiencies, if it's positive, then we've multitask learned. And so this weighted average gives us some flexibility. If we say all the tasks are equally important, then you kind of have to positively transfer on average. If we say other things, we may show that we only care about one of the tasks, or we may care that they all positively transferred. We have all sorts of flexibility in there to characterize different versions of multitask learning. Now, those are all in the context of batch learning, but we also sometimes have more general kinds of things like lifelong or continual learning. This is similar to multitask learning, but it's sequential rather than batch. And so here we're going to assume everything is streaming. The data, the possible actions, the errors, the tasks, and this is really key, that the tasks can be changing over time. And really anything about the task can change over time, including, like, say, the space of possible inputs or the space of possible outputs, things like that. And so, before quantifying this, I just want to clarify something about lifelong learning, which is usually kind of ignored in the field. There's something one can do, which we call lifelong cheating. Lifelong cheating is the following. You store every single data point you've ever seen. And then every time you get a new data point, you literally just update everything in batch mode. Okay? If you do that, you haven't meaningfully lifelong learned in any way. But doing so naively consumes order n space and order n squared time. And so in order for an algorithm to be a bona fide lifelong learning algorithm, it has to take less than n space and or less than n squared time. Otherwise, it's not doing any meaningful transfer in a computationally efficient way. Okay, so given all that, there's two different kinds of transfer that happen in lifelong learning. One is transferring forwards and the other is transferring backwards. So to clarify, we let DS be the set of data points associated with task S, just as we had before. And the D less than S is all the data points that we've seen up to and including the last data point from task S. So if there was a whole bunch of tasks before task S, it includes all the data associated with those tasks. And forward learning efficiency is the ability to improve performance on task S by virtue of leveraging all the data that you've seen in the past. Okay, and so it's just this ratio, and we say it forward learns if the log is positive again. Now, backwards learning is a similar thing, but here now we care about all the data after we've seen this task. So now you have new tasks, and you want to see, did the new task help you in the old task? And so one example of this is, let's say you're learning Beethoven, and then you learn some new arpeggio scales, and then you go back to playing Beethoven. Are you better at Beethoven now by virtue of having trained on the arpeggios after first learning Beethoven? Or to do it in a different context, let's say you're training in soccer, and then you go lift weights, and then you come back, and now are you better at soccer? And so this kind of thing happens in humans and non-human animals all the time. And it's, again, the same exact ratio, but now we've just plugged in different things on the top and the bottom. This is the task data, and this is all of the data. And we say that if backwards learned for that task if the log is positive. And a thing that's important for our perspective is that this is forward efficiency and this is backwards efficiency, and the product of them is just back to task efficiency. So just whether you transferred from all the data for this one task. And so these notions of forward and backwards efficiency, at least from my perspective, are reasonably fundamental in that they kind of just pop out. So what I want to summarize at this point is to say that all the previous notions that we've talked about, and some of which have been characterized in the literature to a certain degree, are all basically special cases of this learning efficiency notion that we have defined, where we just have different things, A and B, to get the different kinds of learning. And so for us, what this means is this learning efficiency notion is very fundamental, and we're going to prove some properties about it shortly. Before that, I just want to say, we've made this table of all the different kinds of learning scenarios, or many of the different kinds of learning scenarios that have been proposed in the literature. And in our paper, we show how each of them can be quantified using this exact same metric. Okay, so now that's great. We have this theory, this framework that allows us to include lots of special cases and problems, but if it doesn't allow us to prove any theorems about algorithms that can converge, it's really going to be limited in certain ways. So we're going to prove a few theorems about that. And first, I just want to talk about classical learning theory, and in particular, there's this very interesting question from the late 80s, which was, is weak learning different from strong learning? Weak learning means that an algorithm can do better than chance on some data, with enough data. And strong learning is that an algorithm can do arbitrarily close to optimal with sufficient data. And it was a question in the late 80s by Valiant, like, are these the same thing or are they different things? In other words, if a problem can be weakly learned, is it necessarily also the case that it can be strongly learned? And Shapiro proved in the early 90s that if a problem is weakly learnable, it's also strongly learnable. And that's basically when he invented boosting, and now we have all the great, beautiful boosting results and gradient boosted trees and things like that. But it's a very counterintuitive theorem from my perspective. Like, the fact that you can learn at all means you could get arbitrarily good. That doesn't feel reasonable. So let's see what happens when we relax this assumption that's implicit in much of classical learning theory, which is that the training distribution is the exact same as the evaluation distribution. Once we uncouple them, some interesting things happen. And in particular, we have this theorem which says, with only out of distribution data, there exist some problems that are weakly but not strongly learnable. Okay, so what this means is that OOD learning is different in kind from in-distribution learning. And for me, it really changes the way that we want to think about getting data, because, as part of this big data revolution, we've been just getting more and more and more data. And if you have this weak learner theorem, which says that all you need is enough data and you'll eventually do perfect, then just keep getting more data and you'll eventually do perfect. But what this says is, well, if the training distribution and the evaluation distribution are different, that's not true anymore. You can't just get more data and be guaranteed to improve. You have to think now about which data you want to get, because different kinds of data will improve, and certain data just literally won't make you improve any further. So for me, that changes the way that we want to think even about getting bigger and more data, because we want to think more carefully about what kind of data. The next theorem is about about the relationship between this transfer learning or this learning efficiency and weak learning and strong learning. So we've already just shown that weak learning is weaker than strong learning in this OOD setting. But theorem 2 says that positive learning efficiency is even weaker than weak learning. In other words, weak OOD learnability implies positive log learning, but not necessarily vice versa. So for me, this means that positive learning efficiency is kind of a fundamental property of learning problems, because if you can learn at all, then you can do this. And you might not be able to weakly learn, and you certainly might not be able to strongly learn. But learning at all seems to me, at least from my understanding of the existing definitions, this is the weakest version of learning that I know, and it seems to satisfy the intuition that Tom Mitchell really proposed, which is if you do better at a task because you have some data, then you've learned with respect to that task by virtue of that data. Okay, so that's some theory. There's obviously many limitations associated with that theory, but it's a start. And now I want to talk in the last few minutes about how we can improve practice. So going back to lifelong learning, there's a paper from about 30 years ago from the cognitive sciences literature, really, which is talking about catastrophic interference, or what's also called catastrophic forgetting. And the idea is if you train a machine learning model on some task and then you train it on a new task, it forgets how to perform the old task. And that is called catastrophic interference or forgetting, and it was a big problem. And since then, there's been many, many papers. I mean, it's been 30 years, including many papers from some of the authors, some of the other speakers here, and lots of really beautiful work about how to overcome these things. But it's still an unsolved problem, in my view. And I think one of the issues has been that previous work set the bar too low. They've been all trying to solve this catastrophic interference, like not forgetting so much. But as I said before, humans and non-human animals have this property that when you learn a new task, it can actually improve performance on past tasks, not just make it so you don't forget much, right? And this is the whole deal with cross-training that anyone who's played any competitive sports knows very well. You cross-train and it can improve performance. And so what we say is we want a lifelong learner not just not forget, but it should exhibit both positive forward transfer and positive backward transfer for every task. That would be the ideal. And so that's what we set out to do. And so we came up with this approach. It's really very simple and closely related to a lot of other things, but I think amazingly effective. And the deal here is that it's based on kind of like boosting and random forest, but in those approaches, what you do is you ensemble the outputs of each tree in that case, or each weak learner. So you have many weak learners and you ensemble each of those outputs, maybe by averaging or whatever, and you get some prediction. But as we know now, each of those weak learners, if they're not like a linear discriminant, but something more interesting, will have an internal representation. And that internal representation has a much richer representation of the data than just the final output, which is always a scalar. And so rather than ensembling the decisions, one can ensemble the representations. And insofar as each representation has complementary information about the task, then you can leverage them effectively and get better performance by ensembling them. And so, we're running low on time, so I'll skip this slide mostly, but just to say we've run some simulations and we're able to show in very clear cases that there's positive transfer for our algorithms and not so for kind of more naive settings. Well, then we ran it on a very popular kind of modern data set, the CFAR 10 by 10, which is a variant of the CFAR 100 data set, but rather than having just one task with 100 classes, there's 10 tasks, and each one has 10 classes. And each class has 500 training samples, and we train it like that. And so what you can see here is this slide shows the forward transfer properties. We have two different algorithms that we designed. The blue one is called ODIN. It's the omnidirectional network, because we're ensembling networks. And the red is omnidirectional forest, because we're ensembling forests. And what you can see on the x-axis is the number of tasks seen, and on the y-axis is the log of the forward transfer efficiency. And so what this shows you, for example, is task 2 we do about, 0.5, like 5% better on task 2 by virtue of having seen task 1 data than we would have had we only seen task 2 data. And as you keep going up, by the time we get to task 10, we're doing about 20 to 25% better on task 10 by virtue of seeing task 1 through 9 data. This means we're really transferring forward. There's another algorithm, progressive neural networks, which is very similar and inspired a lot of our work, that also exhibits positive forward transfer here. But this other algorithm, DFCNN, which is another recent lifelong learning algorithm, has no positive transfer. And this is actually one of the problems we noticed in the literature from our view, is when people quantify performance in terms of accuracy, it can be very confusing whether they've successfully transferred information across tests, which is the real question. And so this metric allows us to be really precise and say, yes, we have or have not transferred. On the right, I'm showing a bunch of algorithms that have a different set of constraints, which is that they didn't allow for the representation to grow in size. And so we have a forest version that also has that property where it doesn't grow in size. And what you can see is all the other algorithms, they're doing reasonably well insofar as they're not forgetting everything, and that's great. But ours is the only algorithm that's actually able to transfer forward without growing in representational size, at least of the algorithms that we compared to. There's a similar thing with backwards transfer, and so here on the left is the number of task scenes, and on the y-axis is the log backwards transfer efficiency. And what you can see here, for example, of task 2, is once we get task 3 data, task 2 is doing better. And once we get task 4 data, task 2 performance is getting better. And in fact, it's essentially monotonic. For every single task, as we get more and more data associated with other tasks, the performance on the earlier tasks is also improving. And what you can see is the progressive neural nets is not transferring backwards at all. DFCNN is forgetting. And then again, we have the resource constraint versions where essentially everything else is forgetting, and we're transferring forward for the most part, although not as monotonic as before. So in my view, we have a nice start on all 4 of these goals, and yet there's very severe limitations to everything we've done. So in terms of the formal theory, what we really want is convergence guarantees, to say if we get this amount of training samples and this amount of evaluation samples, and they're both growing at different rates, what kinds of algorithms have performance guarantees for those settings, and what are the conditions on the kinds of distributions and the relationship between the distributions that have that property. Although we've included lots of different learning scenarios, the biological learning, where there's really no tests, doesn't quite fit into this framework yet. I think it will enable lots of rich theory. So far, it's provided some theory and no real streaming or reinforcement learning theory yet. And then in terms of the practice, I think our algorithms are interesting, but there's many unsolved problems, like, for example, should we grow resources or not for a given new thing? Or what if the task isn't provided to you, and things like that. I'll skip future directions for time purposes and just say we have a bunch of publications on this stuff, and I'd like to acknowledge my family, all the collaborators. This is also done in collaboration with Microsoft Research, funded by L2M, and then I'm happy to take any questions. Thank you.
Thank you very much, Josh. I guess I'm going to pass the call for questions.
Okay. So thanks, Josh. I'm going to start with a question from the question box. The most upvoted one comes from Francisco Cervantes. And the question is, about storing, what is the formal mapping between learning and memory? Does memory come prior to learning, or is it the other way around? Different formal types of memory may imply different formal types of learning.
That's a very interesting question. So if I understand it correctly, and I'm happy to talk more offline, I think memory is formed by learning, at least within a lifetime. But then there's different kinds of memory which are across lifetime, kind of encoded by the genetics in the genome. And so that kind of memory, there's evolutionary learning, but not necessarily within lifetime learning. Like, for example, we learn things like convolutions are useful for vision, and so we kind of have them in our eyes. I'm not sure if that really answers your question, and I'd be happy to speak more offline if I didn't get it right.
Well, there's a follow-up to that from Vail Borghesani. How does that map to the brain? It reminds me of the teacher-student framework of Sachs et al., trying to explain the interplay of hippocampus versus cortex. I don't know if that is a question you can comment on.
Yeah, so the way we've been thinking about this in terms of the brain is more from a developmental perspective rather than trying to explain the interplay between different neuroanatomical regions. And so the way we think about it is, and developmentally in the juvenile setting, we're growing resources. And so we're establishing kind of weak learners that can essentially learn important primitives. And then in the adult phase, there's no more learning of weak learners, but there's lots of ways of ensembling them that can be interesting and enable lots of different complicated processes. And then as we age, we start losing the ability to ensemble and also some of the weak learners. And so we need to reallocate resources appropriately to make sure we don't forget how to breathe, but we do remember, but we may forget other stuff, basically. So I don't know how that has an interplay with hippocampus and cortex, but I imagine hippocampal things are going on as we age in different rates as cortex, and I'm sure there's implications there. It'd be interesting to talk about later.
Okay, thanks. Another question posted by Max Pelmatuzo was, how does this metric of learning efficiency relate to statistical efficiency, i.e. estimator variance relative to the best possible Kramer-Rao for the given sample size? Efficiency there leverages a bound. Have you thought about bounds on this metric?
Yeah. Max, I love that question. Thank you so much. So actually, learning efficiency was directly inspired by relative efficiency. So for those of you who don't have a lot of formal training in statistics, relative efficiency, it compares two different estimators on the same problem. And the deal is, if they're both unbiased, you can just look at the variance of their estimate, and you want to use an estimator that has a smaller variance. This is a slightly different thing because it's the same estimator on two different data sets. One is a smaller one that only has the training data, and the other is a bigger one that also has all this out of distribution data. And so it's a slight variant, but it's very closely related. And we have thought a lot about upper bounds. And in certain contexts, what we can show is that an upper bound is given by, if you let all the out of distribution data actually be sampled from the same distribution as the training data, then you can transfer the most possible because there's the most amount of information there. That depends on some assumptions that we haven't quite formalized yet and worked out the details, and would love to do that with you and anybody else if you're interested.
I actually had a question, and it might be a very naive one, but you mentioned at one point that in out-of-distribution learning, because the training and testing distributions are different, getting more data is not so useful, and what we really need is to prioritize the kind of data that will be most helpful. So I'm wondering if you can comment. I mean, do you have any suggestions on how can we prioritize? Is there a formal way of saying what kind of data we need to be able to go beyond if possible?
Yeah, it's a great question, and we have no satisfactory formal answers to that yet. And what I can say is, if we think about the uncertainty, say we're trying to estimate some, like a Gaussian. So there's two parameters, there's a mean and a variance. We can look at the uncertainty we have about our estimates of the mean and the variance, say from a Bayesian perspective, because there'll be some posterior on our estimate of the mean and the variance. We want to get data that reduces the uncertainty the most about the parameters that we care the most about. Right. So sometimes we won't care so much about the variance, and so we'll just focus our energy on getting more samples to be informative about the mean. If we care about the variance, then we want to sample more to get information about that.
Right. It's a little bit like Simon's procedure that he's using. Okay. One last question from the audience, from Zerai Abderazek, who asks, how can we associate cognitive performance and learning with physical activity in adult brain and learning contexts?
I'm not sure I entirely understand that question, but I would say is that one idea we have recently about kind of evaluating performance in human and non-human animal learning is designing experiments that are essentially homologous across different species and also the machines. So for example, we can design a maze that humans can play as a video game. Rats can then actually do, like, walk around the physical maze, and then bots can also explore the maze. And so we can quantify performance on lots of different things in the same setting to the extent possible and evaluate how well humans and machines are doing relative to, say, rats or jumping spiders or mice or whatever other things.
Okay, one more, since we still have a little bit of time. Lauren Pernet asks, what do you think of the theory that the function of dreams is to learn to generalize? Would that fit with out-of-distribution generalization? And is there a link to lifelong cheating?
That's a really fun question. So I don't know enough about dreams to have a coherent answer, although I think some of the other speakers in the next few days do. For me, though, what I would say is dreaming is kind of like a replay of possible past or possible futures. And so I think about dreaming as serving the role of doing kind of counterfactual causal inference, trying out different outcomes that didn't happen and trying to intervene in different ways, simulating that, and seeing if we can build up a better causal model of the world by virtue of exploring all the different counterfactuals in simulation that we couldn't have actually explored in the real world. And then in terms of lifelong cheating, that's a concept that's really related to computational resources. Just if you store everything, then you're not doing lifelong learning in a meaningful way. That's obviously animals aren't storing everything they've ever seen and retraining their brain from scratch every time they get new data. So if your algorithm does that, it's not doing bona fide lifelong learning.
Right. Again, and we have a question from Guillaume Lajoie, who asks if there is any hope in adapting this learned structure transfer metric for more complex tasks and data sets. Is there hope to approximate this metric for more flexible use?
Yeah, so that's a great question. From my perspective, the whole point of the metric is it can readily be applied to arbitrarily complex tasks. You just have to evaluate it per task and then choose how you're going to weight the average across tasks. And so I think it's very flexible already. Sorry if I failed to communicate that effectively, but if you want to talk about that more offline, I'd be very happy to, and I'd love to learn how to communicate that more clearly.
Okay, well, actually, it may be that he asked the question just before you answered it, because that's the way this works. So Guillaume probably understood that. He's clapping. All right, well, anyway, with that, I think we need to move on. We've decided, because of various technical delays, because we've gotten behind time, we're going to skip the break. We're sorry about that, but we want to move on right away to the next speaker, Jim DiCarlo. So I'll let Andrea introduce.
Well, thanks again, Josh. It was a great talk, and I look forward to talking to you more about some of this work a little bit later. So thanks again.